So I wanted to do a little video working with RC circuits. We learned some of these relationships for combining a resistor and a capacitor in a circuit. Basically, there can be two things that we want to do. We might be trying to charge the capacitor, in which case we are combining the capacitor, a resistor, and a power supply or a battery. And what we find is that gradually over time, the charge on the capacitor will grow. As it does, the current through the resistor will fall because of the fact that the potential difference across the capacitor will start to grow, which means the potential difference across the resistor has to fall. Eventually, when the capacitor is fully charged, it will have the entire potential difference of the battery and no current will flow anymore. For these uses, we use the sort of script E to represent the EMF of the battery, just to make it clear what we're talking about. We also are able to discharge a capacitor. When we do that, we start with a capacitor that's already fully charged, but we connect it in series with a resistor, but we don't have a battery. We're actually just allowing the capacitor, by connecting wires to either plate, for those charges to leak off of the plates through the resistor, keeps it from happening instantaneously. And so that's discharging a capacitor. So of course the charge is going to decrease over time. At the same time, so does the current. We usually use this negative sign for the current when we're talking about discharging a capacitor, simply because the nature of the situation is that the current that flows in a circuit where the capacitor is discharging goes in the opposite direction from the way it does when it's charging up. That's what that negative sign is about. So sort of, we will derive these expressions in class, and that whole process can be kind of confusing because of the math that's used. But I wanted to sort of emphasize the fact that once we have these expressions, we don't have to derive them again and again. And so I gave an example, basically just picked an example out of the back of the book of the type of problem we might be able to do. So in this particular problem, we have a 500 ohm resistor, an uncharged capacitor with a capacitance of 1.5 microfarads, and an EMF or a battery that has potential of 6.16 volts. We're going to connect them all in series. Because we have the battery, it means that we are actually charging this capacitor. Then the questions that are being asked is, what is the initial current? What is the time constant of this circuit? What is the current after one time constant has passed? What's the voltage after one time constant has passed? And how long will it take to reach half of the maximum charge? Because we're not going to be dealing with any discharging of the capacitor, I'm going to get rid of these expressions for now, just to give us a little bit more room to work. So the first question asks what the initial current is. When we begin with charging the capacitor, because the capacitor doesn't have any charge on it, it doesn't have a potential difference across the plates. And that means that the entire potential difference of the circuit is found on the resistor. And then using Ohm's law and knowing the potential difference of the battery, we can solve for the current. It's the potential difference of the battery, which is the same as the potential difference across the resistor the instant we begin, divided by the resistance. So for this, we do 6.16 volts divided by 500, and I get an initial current of 12.32 milliamps. Milli would be 10 to the minus 3. The second question asks us to find the time constant. We use the letter tau to represent the time constant. You can see it in these equations. It's sort of part of the exponent of E. And also you can see in the alternate expressions that I wrote, it's equal to the resistance times the capacitance. The time constant just represents sort of an increment of time that's important for this particular circuit, kind of gives you a sense of how quickly it's going to charge up and also how quickly it would discharge. It does mean that the units of resistance times capacitance, when you work it all out, will end up, the product will give you units of second, because of course the exponent of E can't have any units. It has to be a pure number. So here the resistance is 500 ohms, the capacitance is 1.5 microfarads, and so we get a time constant of 7.5 times 10 to the minus 4 seconds. We could have also expressed that as 75 or 0.75 milliseconds. Okay. Now, the next question says, what is the current after one time constant? So we're going to look, the current is equal to I naught e to the minus t over tau. And so what they're telling us to do is to replace the time by tau. So we already found I naught. It was 12.32 milliamps. And then tau over tau, I don't really even have to write it out. It's 12.32 e to the minus 1. And so we find that the current after one time constant has dropped down to 4.53 milliamps. Okay? And so we got that. The other question they're asking is, what is the voltage after one time constant? So the voltage can be expressed as Q over C. So I need to find the charge at one time constant. So I'm just going, I'll do it here. So Q will be equal, the total charge of the total charge that ever, the maximum charge that's going to be on the capacitor is going to be equal to, the total charge that's going to be on the capacitor is the capacitance times the EMF of the battery. So this is the expression we're going to use, but we want to let T be equal to tau. So this is going to simplify into the capacitance times the EMF, that's the battery, 1 minus e to the minus 1 again, because we're finding it's e raised to the tau over tau, with that negative sign, of course. And if I replace the values of capacitance and the EMF of the battery, I find that this charge that is there after one time constant is 5.84 times 10 to the minus 6 coulombs. And so if I take that charge, so I put that there, over the capacitance, which is 1.5 microfarads, I get a voltage of 3.89. So in a sense, what you're getting, you can kind of think about is this is the potential difference across the capacitor after only this amount of time has passed. Initially it was 0. It's eventually going to reach a maximum value of 6.16 because when the capacitor is fully charged, all of the potential difference will be across the capacitor because there won't be any current flowing in the circuit. So already it's gotten up to over half of its goal potential, if you want to think of it that way. And that's in a really short time. So you can see that, if we wanted to charge a capacitor up in a certain amount of time, we could really control how quickly that happens by altering and controlling the resistance and the capacitance that we work with together. And now finally, the last thing we're going to do, and so I'm going to erase the current equations just so I have a little more room to work, is how long does it take to reach 1/2 of the maximum charge? So again, you can see the expression for charge right here, and what we're saying is that at some instant in time, the charge that we get is going to be 1/2 of this maximum charge. And that's what we're trying to figure out, like when is that going to happen? And this just involves some math that we might not do that often, which is part of the reason I wanted to do it for this video. If I divide both sides by q, I get 1/2 is equal to 1 minus e to the minus t over tau, and which I'm just going to write as RC, just to remind us that that's what tau is. And so if I sort of rearrange things, I can get e to the minus t over RC is equal to 1/2. I'm basically going to bring this term over here and bring the 1/2 over here. Now, we are trying to find the time, but the time is in the exponent of e. And so what we do is we're going to take the natural log of both sides. When we do that, so I'm just kind of, this isn't really very nice notation, but just to remind you what we're doing is taking the natural log of both sides. When I take the natural log of e, I just simply get the exponent that it has. And here I have the natural log of 1/2. If you remember, you might not, it's okay, that when we take the natural log of a decimal, it's going to be negative, and so you shouldn't let that negative sign bother you because it'll all work out. So t is going to be equal to minus RC times the natural log of 1/2. And when we put in our values for the resistance and the capacitance, we find a time of 5.19 times 10 to the minus 4 seconds, or 51.9 milliseconds. All right. And so that's just an example of how we might use the equations that we derive for RC circuits to sort of find out different pieces of information about what's happening as we charge up a capacitor. We could certainly do the same thing with discharging a capacitor, but we would have to be sure that we did use the equations that were specific to that scenario.